this section, we're going to study series still that have both positive and negative terms, and the simplest such series is what we call an alternating series, whose terms alternate in sign. So an example of this would be something like negative 1/2 to the nth power. So if you were to actually list out the terms of this, you would have negative 1/2 to the 0 power plus negative 1/2 to the first power plus negative 1/2 squared plus negative 1/2 cubed, so on and so forth, which would give you 1 minus 1/2 plus 1/4 minus 1/8 plus so on and so forth. And you could see that this thing is changing sign back and forth from positive to negative. Another way that it could be written is the sum from 0 to infinity of splitting out the negative and the 1/2, negative 1 to the nth power times 1/2 to the nth power. But this is an alternating geometric series where r is equal to negative 1/2. Now, with this one, because the way geometric series work, obviously you could look at the absolute value of r and see that this is less than 1, and that means that this series is going to converge. But there's another test that you can use with alternating series that would work as well. So there are two possibilities for alternating series. Either the odd terms are negative or the even terms are negative, and that's all based on the powers within the series. So if you have something like a sub n, which is positive, and then you've got this behavior here with the negative 1 to the n or negative 1 to the n plus 1, for this one the odd powers will be negative, and for this one the even powers will be negative because of that plus 1 feature. So these series converge when two conditions listed below are met: when the limit as n approaches infinity of a sub n equals 0, and a sub n plus 1 is less than or equal to a sub n for all n. So think about what's happening in these types of series. You start out with a number and you subtract a little bit, and then you add a little bit of that back, and then you subtract a little bit, and it keeps just adding and subtracting a little bit less each time until you eventually are zeroing in on a number, and that's what it could converge to. So let's look at an example. It says determine the convergence or divergence of negative 1 to the nth power over 3 to the nth power. Now yes, you could look at this one as a geometric series, but we're going to look at it as an alternating series. So this one I'm going to write as the sum from 1 to infinity of, instead of negative 1 to the n over 3 to the n, we're going to put negative 1 to the n and 1/3 to the n, because this is going to be our a sub n. So for number 1, I'm just going to verify that the limit as n approaches infinity of a sub n, which is the limit as n approaches infinity of 1/3 to the n, or 1 over 3n, and let's just write it like that, 1 over 3 to the n. 1 over 3 to the nth power is going to be 0, which is what we want, because we would have a denominator that's growing, heading towards infinity, and a fixed number on top, so that gives us 0. Number 2, we need to show that a sub n plus 1 is less than or equal to a sub n for all n. So I'm going to start with the fact that n is less than n plus 1. Which means that if I raise 3 to the nth power, that's a smaller number than I would get by raising 3 to the n plus 1 power, because 3 is greater than 1, so the bigger power is going to make that term grow. And then if I were to divide by both of these terms, I would get that 1 over 3 to the n plus 1 is less than 1 over 3 to the n. And of course, this is my a sub n plus 1, and this is my a sub n, which is what I want. So by the alternating series test, we can say that the sum from 1 to infinity of negative 1 to the n over 3 to the n converges. This one is the sum from 0 to infinity of negative 1 to the n plus 1 over n factorial. So we're going to take a similar approach. I'm going to write it as negative 1 to the n plus 1 times 1 over n factorial, so we'll call a sub n 1 over n factorial. So I'm going to verify that the limit as n approaches infinity of 1 over n factorial is equal to 0, which it is because you've got a fixed number over something that's getting really, 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 really big. We're going to take that same approach we took last time. We know that n is less than n plus 1, so that means the factorial of n plus 1 is going to be larger than the factorial of n. This should make sense to you. Think about numbers. If you plugged in a 4 here and a 4 here, you would have 4 factorial is less than 5 factorial. That's going to be true. And so 1 over n plus 1 factorial is less than 1 over n factorial, so that means that a sub n plus 1 is less than a sub n. So this is decreasing. And we can say by the alternating series test, our sum converges. It is important to note that if either one of these two conditions is not met, that doesn't necessarily mean that the series diverges. It just means that you cannot use the alternating series test. So again, the alternating series test is not going to tell you whether a series diverges. It'll only tell you if it converges. Another concept here is the alternating series remainder. If a convergent alternating series satisfies the condition a sub n plus 1 is less than or equal to a sub n, then the absolute value of the remainder r sub n involved in approximating the sum s by s sub n is less than or equal to the first neglected term. So that says that if s minus that partial sum is going to be equal to the remaining neglected or equal to the r sub n, which is the remainder here, and that's going to be less than or equal to whatever the next term is. So what this allows you to do is get an approximation for the actual sum of a series if you can figure out part of the series. So I'm going to find, it says approximate the sum of the series by the first 6 terms. So I'm going to find s sub 6, which we know is a1 plus a2 plus a3 plus a4 plus a5 plus a6. So this will be, let's see, negative 1, 1 plus 1 would be squared over 1 factorial, plus negative 1 cubed over 2 factorial, plus negative 1 to the 4th power over 3 factorial, plus negative 1 to the 5th power over 4 factorial, plus negative 1 to the 6th power over 5 factorial, plus negative 1 to the 7th power over 6 factorial. So that gives me 1 minus 1/2 plus 1/6 minus 1 over 24 plus 1 over 120 minus 1 over 720. You could do the arithmetic on that. And if I add all of those together, I get 91 over 144. Okay, great. So that's s sub 6. Well, what we know from this theorem is that s minus s sub 6 has to be equal to r sub 6, which is the remainder, and we know that that is less than or equal to a sub 7 if I plug in a 6 here. This is what we're trying to estimate. This is the actual sum, and we can do that by plugging the numbers we know into this and solving this inequality. Well, a sub 7 is pretty easy to calculate. That's negative 1 to the 7 plus 1 power over 7 factorial. So that is 1 over 5040. So I get that s minus s sub 6 is less than or equal to 1 over 5040. And what this allows me to do, because I have an absolute value less than or equal to a number, I know that s minus 91 over 144 has to be between positive 1 over 5040 and negative 1 over 5040. And then I can just solve this inequality here by adding 91 over 144 to all of these pieces. And if you do the arithmetic on that, that will tell you that s has to be between 199 over 315, and 177 over 280. Now, it didn't ask us to find a decimal approximation. This doesn't tell you a whole lot unless you deeply understand fractions. But just to show you how close this actually is getting, if you put this into a calculator, this is approximately 0.6299, and this is approximately 0.6339. So that's pretty close, and it's a pretty good approximation, but it gives you an upper and a lower bound for what S could potentially be. And of course, because of the way alternating series work, the higher your n is, the higher the number you start with here, the more accurate your prediction is going to be. So let's look at the next type of problem. It says, determine the number of terms required to approximate the sum of the series, the sum from 1 to infinity of -1 to the n plus 1 over n to the fourth power with an error of less than 0.001. So I'm just going to verify a few things here. If I let a sub n be equal to -1 to the n plus 1 power, or sorry, a sub n is just going to be the 1 over n to the fourth. And we have that alternating portion with the -1 to the n plus 1. I'm going to just make sure it does actually converge. So the limit as n approaches infinity of 1 over n to the fourth power, constant over infinity, that gives me 0. And I can look at this and I can tell that this is going to be a larger denominator than this, so this is true as well. So by the alternating series test, that looks kind of funny. There we go. We can say that the sum from 1 to infinity of -1 to the n plus 1 over n to the fourth converges. So we do know that it converges to a number. That's good. What we need is an n such that a sub n plus 1 is less than 0.001. Because what we want is that s minus s sub n to be less than or equal to a sub n plus 1, which we want to be less than 0.001. So all I'm going to do is I'm going to plug in n plus 1 where I have this little n here. So a sub capital N plus 1 would be 1 over n plus 1 to the fourth power. And we want that to be less than 0.001. So if I were to set this up as a fraction over 1, what I can do is I can cross multiply this because all of these things are positive. And I get that 1 is less than 0.001 times n plus 1 to the fourth power. And then I can divide by 0.001. Again, positive, so there's nothing wrong there. And I get that 1 over 0.001 has to be less than n plus 1 to the fourth power. I can take the fourth root of both sides, or before we do that, 1 over 0.001 is 1,000. And now I can take the fourth root of both sides. And the fourth root of 1,000 is about 5.623, which is less than n plus 1. So if I subtract 1 from both sides, I get 4.623 has to be less than n, or n has to be greater than 4.623. Now we know that n has to be an integer because we're looking at a series, and so we don't use any non-natural number or non-whole number numbers for our input. So you just always want to round this up no matter what the decimal point. Even if the decimal point is less than 5, if it tells you that you need n to be greater than that, we're just going to round up to the next integer. So in order for this to work, to have this level of accuracy, you need at least 5 terms. And if you do that, then you can use the process that we looked at in the last problem and get an estimation that's within that 0.001.